Welcome to Math with Mr. J. In this video, I'm going to go through a mini course on solving one-step inequalities. We will go through examples that include addition, subtraction, multiplication, and division. Everything is put into chapters and time-stamped, so feel free to jump around. We will start with addition inequalities and go from there. Now, when we solve inequalities, we want to isolate the variable, get it by itself on one side of the inequality. We do that by using inverse operations. So this is very similar to when we solve equations. One thing we need to be aware of, though, when it comes to inequalities, we flip the inequality symbol when multiplying or dividing both sides by a negative. And we will talk more about this later in the video. Let's jump into number 1, where we have w plus 7 is greater than or equal to 15. So we need to solve this. We need to isolate that variable of w. Now we are adding 7 to w, so we need the inverse operation of addition. The inverse operation of addition is subtraction. So let's subtract 7 from the left side of the inequality. Whatever we do to one side of an inequality, we must do to the other in order to keep it balanced. So subtract 7 from the right side as well. Now, as far as the left side, these 7s cancel each other out. W is now isolated, so we have w is greater than or equal to, and then on the right side, 15 minus 7 gives us 8. So we have w is greater than or equal to 8. So any value greater than or equal to 8 is a solution of this inequality. It makes it true. And let's check a solution to make sure we are correct here. Now we can't check every value greater than or equal to 8. That would be impossible. We have an infinite amount of possibilities as far as solutions, values that make this inequality true. So what we can do, we can check one value, or more if we would like, to see if this works. Let's use 10. 10 is greater than or equal to 8. So let's plug in 10 for w. So we have 10 plus 7 is greater than or equal to 15. 10 plus 7 gives us 17. 17 is greater than or equal to 15. So 10 does make this inequality true, along with any other number greater than or equal to 8. So we are correct here. Our answer for number 1, w is greater than or equal to 8. Let's move on to number 2, where we have x plus 4 is less than 9. So we need to isolate that variable of x. We are adding 4 to x, so we need the inverse operation of addition. That's subtraction. So subtract 4 from the left side. Whatever we do to one side, we have to do to the other. So subtract 4 from the right side as well. These 4s cancel each other out. X is now isolated, so we have x is less than, and then on the right side, 9 minus 4 gives us 5. So x is less than 5. So any value less than 5 is a solution of this inequality. It makes it true. Let's check one so we can pick any number less than 5. Let's use 3. So plug in 3 for x here. So we have 3 plus 4 is less than 9. 3 plus 4 gives us 7. 7 is less than 9, so we are correct here. Our answer for number 2, x is less than 5. So any value less than 5 will work for this inequality, will make this inequality true. So there's how to solve one-step addition inequalities. Let's move on to subtraction. So here are our subtraction examples. Let's jump into number 1, where we have y minus 2 is greater than 5. So we need to solve this. We need to isolate the variable of y. Now 2 is being subtracted from y. So we need the inverse operation of subtraction. The inverse operation of subtraction is addition. So add 2 to the left side of the inequality. Whatever we do to one side of an inequality, we must do to the other in order to keep it balanced, so add 2 to the right side as well. Now, as far as the left side, these 2's cancel each other out. So y is now isolated. We have y is greater than, and then on the right side, 5 plus 2 gives us 7. So y is greater than 7. And that's our answer. So any value greater than 7 is a solution of this inequality. It makes it true. And let's check a solution to make sure we are correct here. So we need to use any value greater than 7 here and plug it in for y. Let's use 12. So plug in 12. We have 12 minus 2 is greater than 5. 12 minus 2 gives us 10. 10 is greater than 5, so this does work. We are correct here. Our answer, again, for number 1, y is greater than 7. Let's move on to number 2, where we have -6 is less than or equal to c minus 3. So we are subtracting 3 from c here. We need the inverse operation of subtraction. That's addition, so add 3 to the right side of the inequality. That means we need to add 3 to the left side as well. Now, as far as the right side, these 3's cancel each other out. C is now isolated, so we have C is greater than or equal to, and then on the left side, -6 plus 3 gives us -3. So C is greater than or equal to -3. Now, one thing we can do here is rewrite the inequality with the variable coming first. It can make it easier to work with inequalities, so keep this in mind. And all we need to do is flip it. So we need our variable c, and then our symbol we need to make sure is going the correct way. So it's opening up towards c. We need c to be greater than or equal to -3. So again, we can rewrite this with the variable coming first if we prefer. Now let's check a solution. So we need any value greater than or equal to -3. Let's try 4. So we will plug in 4 for c. So we have 4 minus 3. 4 minus 3 gives us 1. And -6 is less than or equal to 1, so that does work. Our answer for number 2, C, is greater than or equal to -3. So C can be any value greater than or equal to -3. So there's our subtraction section. Let's move on to multiplication. Here are our multiplication examples. Let's jump into number 1, where we have 5x is less than or equal to 10. We need to isolate x. X is being multiplied by 5, so we need the inverse operation of multiplication. That's division. So divide the left side of the inequality by 5. Now, whatever we do to one side of an inequality, we must do to the other in order to keep it balanced. So divide the right side by 5 as well. Now, as far as the left side, these 5's cancel each other out. X is now isolated. So we have x is less than or equal to, and then on the right side, 10 divided by 5 gives us 2. X is less than or equal to 2. So any value less than or equal to 2 is a solution of this inequality. It makes it true. And let's check a solution to make sure we are correct here. Let's use 1. 1 is less than or equal to 2. So plug in 1 for x. So 5 times 1 is less than or equal to 10. 5 times 1 gives us 5. And 5 is less than or equal to 10. So we are correct here. Our answer, again, x is less than or equal to 2. Let's move on to number 2, where we have 36 is greater than negative 4a. So we need to isolate that variable of a. It's being multiplied by negative 4, so we need the inverse operation, division. So divide the right side by negative 4. That means we need to divide the left side by negative 4 as well. Now remember, when we multiply or divide both sides by a negative, the inequality symbol flips. So as soon as both sides are multiplied or divided by a negative, that symbol flips. And here we are dividing both sides by negative 4. As far as the right side, these negative 4s cancel each other out. So a is now isolated. We have a, and then the symbol flips, and then the left side, 36 divided by negative 4, gives us negative 9. So a is greater than negative 9. That's our answer. And we can rewrite this with the variable coming first if we would like. This can make it easier to work with an inequality. All we need to do is write the variable first. So a. Then we need to make sure the symbol is going the correct way. That's very important. It's opening up towards a here, so a needs to remain greater than negative 9. Either way is correct there, just something to keep in mind. Now, as far as flipping the inequality symbol, we're going to talk more about that and why we need to do that after we wrap up number 2. So again, our answer a is greater than negative 9. So a can be anything greater than negative 9. Now let's check a solution and let's use 0. So plug in 0 for a. We have 36 is greater than negative 4 times 0. Negative 4 times 0 gives us 0. And 36 is greater than 0, so we are correct here. A is greater than negative 9. Now, before we move on to division, let's take a look at flipping the inequality symbol and why this happens when we multiply or divide both sides by a negative. Let's take a look at flipping the inequality symbol and why this happens when we multiply or divide both sides by a negative. Let's start with the example 4 is less than 8. Is this inequality true? Of course, 4 is less than 8. Now let's divide both sides by positive 2 and see if this remains true. And let's rewrite this inequality so we have 4 is less than 8, and we are dividing both sides by 2. On the left, 4 divided by 2 gives us 2, and then on the right, 8 divided by 2 gives us 4. So we have 2 is less than 4. So does this inequality remain true? Yes. Now let's divide both sides by negative 2 and see what happens. And we will rewrite the inequality here. So we have 4, and then I'm not going to put the inequality symbol quite yet because we're dividing both sides by a negative, negative 2. And dividing both sides by a negative is going to change the inequality. So we have to flip the inequality symbol, change its direction for this to be true. So we have 4 divided by negative 2 is greater than 8 divided by negative 2. As soon as we divide both sides by a negative, that symbol flips. It changes direction. And that's because 4 divided by negative 2 is negative 2. And then 8 divided by negative 2 is negative 4. Negative 2 is greater than negative 4. So for that inequality to remain true, that symbol flips. So again, negative 2 is greater than negative 4. Now what if we did not flip that sign? Well, we would get negative 2 is less than negative 4. Is that true? No. So notice the difference between dividing by a positive 2 and a negative 2. Now let's apply this to number 2, the number 2 that we already solved. We have 36 is greater than negative 4a. So we need to isolate a by dividing both sides by negative 4. So let's rewrite this. And we have 36 divided by negative 4. And then since we are dividing both sides by a negative, the inequality symbol flips. And then we have negative 4a divided by negative 4. As far as the right side, these negative 4's cancel each other out. A is now isolated, so we have a is greater than, and then on the left side, 36 divided by negative 4 gives us negative 9. So a is greater than negative 9. Now, when we solved this before, we didn't rewrite everything. We divided both sides from the original problem. We flipped after dividing, and we ended up with the correct answer. And that was fine. But here I wanted to rewrite this to show that technically the symbol flips the moment both sides are multiplied or divided by a negative. So we wrote out that step to show that. Now, if you forget to flip the symbol, when you go to check a solution, you'll notice that it won't work. So it's important to check, and then you can catch that mistake. Again, just remember, flip the inequality symbol when multiplying or dividing both sides by a negative. So there's our multiplication section. Let's move on to division. Here are our division examples. Let's jump into number 1, where we have d divided by 10 is greater than 6. So we need to isolate that variable of d. It's being divided by 10, so we need the inverse operation of division. That's multiplication. So let's multiply the left side of the inequality by 10. Whatever we do to one side of an inequality, we must do to the other in order to keep it balanced. So multiply the right side by 10 as well. Now on the left side, these 10s cancel each other out. So d is now isolated. We have d is greater than, and then on the right side, 6 times 10 gives us 60. So we have d is greater than 60. So any value greater than 60 is a solution of this inequality. It makes it true. And let's check a solution to make sure we are correct here. Let's use 70. 70 is greater than 60, and we'll work with that 10. So let's plug in 70 for d. So we have 70 divided by 10 is greater than 6. 70 divided by 10 gives us 7, and 7 is greater than 6, so this does work. We are correct here. D is greater than 60. Let's move on to number 2, where we have x divided by negative 7 is less than or equal to negative 3. So let's isolate x. It's being divided by negative 7, so we need the inverse operation. That's going to be multiplication. So let's multiply the left side by negative 7. And that means we need to multiply the right side by negative 7. Now remember, when we multiply or divide both sides by a negative, the inequality symbol flips. So as soon as both sides are multiplied or divided by a negative, that symbol flips. And here we are multiplying both sides by negative 7. So as far as the left side, these negative 7's cancel each other out. X is now isolated. The inequality symbol has flipped, and then on the right side, negative 3 times negative 7 gives us positive 21. Remember, a negative times a negative equals a positive. So this is our answer. X is greater than or equal to 21. In other words, x can be anything greater than 21 or equal to 21. Now let's check a solution to make sure we are correct here. And let's use 28. That will work with the negative 7 since we are dividing here. So let's plug in 28 for x. So we have 28 divided by negative 7 is less than or equal to negative 3. 28 divided by negative 7 gives us negative 4. So we have negative 4 is less than or equal to negative 3. That is true, so we are correct here. Again, x is greater than or equal to 21. Now, before we end, let's take a look at flipping the inequality symbol and why this happens when we multiply both sides by a negative. This will be similar to what we looked at earlier in the video when we divided both sides by a negative. Let's take a look at flipping the inequality symbol and why this happens when we multiply both sides by a negative. Let's start with the example 2 is less than 5. Is this inequality true? Of course, 2 is less than 5. But let's see what happens when we multiply both sides by positive 2. Let's see if this remains true. And let's rewrite this with both sides being multiplied by 2. Now on the left, we have 2 times 2, which gives us 4. So we have 4 is less than, and then on the right, 5 times 2 gives us 10. So we have 4 is less than 10. So did the inequality remain true after multiplying both sides by 2, positive 2? Yes, 4 is less than 10. Now let's multiply both sides by negative 2. So let's rewrite this with both sides being multiplied by negative 2. But multiplying both sides by a negative changes the inequality. We have to flip the inequality symbol, change its direction. So we're multiplying the left side by negative 2, and then flip the inequality symbol, and then we're multiplying the right side by negative 2. As soon as both sides are multiplied or divided by a negative, that inequality symbol flips in order for the inequality to remain true. Because on the left, we are multiplying 2 by negative 2. That gives us negative 4. And negative 4 is greater than, and then on the right, we are multiplying 5 by negative 2. That gives us negative 10. Negative 4 is greater than negative 10. Now, what if that inequality symbol was not flipped? We would have negative 4 is less than negative 10. That inequality is not true. When we flipped the inequality symbol, that was true. Now let's apply this to number 2 that we already solved. We have x divided by negative 7 is less than or equal to negative 3. So we need to multiply both sides by negative 7. So let's rewrite this, and we are multiplying both sides by negative 7. And since we are multiplying both sides by a negative, the inequality symbol needs to flip. So that inequality symbol needs to change direction as soon as we multiply both sides by a negative in order for this to be true. Now on the left, these negative 7s cancel each other out. X is now isolated, so we have x is greater than or equal to, and then on the right, negative 3 times negative 7 gives us 21. So x is greater than or equal to 21. Now, when we solved this before, we didn't rewrite everything. We multiplied both sides from the original problem. We flipped after multiplying, and we ended up with the correct answer. But here, I wanted to rewrite this to show that technically, the symbol flips as soon as both sides are multiplied or divided by a negative. So we wrote out that step to show that. Like I mentioned earlier, if you forget to flip the inequality symbol, when you go to check a solution, you'll notice that it won't work. So it's important to check, and you can catch that mistake. So there you have it. There's how to solve one-step inequalities. I hope that helped. Thanks so much for watching. Until next time, peace.